Well, cyclovoltammetry is a very important tool, and so we've really just started. We've talked a little bit about it, and what we're going to do is stop and talk about some other topics first, and then we're going to go back to cyclic voltammetry and talk about a number of situations that arise, particularly, well, as I said, for chemical processes that occur when we're doing electron transfer. And so we'll talk about using cyclic voltammetry to help determine rate constants and electrode mechanisms in particular. But for now, let's let CV lie for a minute, and let's move on to another topic. And that another topic is in chapter 12. So we've skipped ahead a number of chapters, and then we'll come back a little bit later to the next chapter on the list. Since we're sort of switching chapters here, why don't we take this time to take a break, and then we'll start again in a minute. So I'm going to take a break. All right, we're back. Let me start this by saying chapter 12 is a chapter that has to do with the double layer and about adsorbed species. And those two right offhand might not seem to be very much linked, but as we'll see, they are quite linked in this treatment of the double layer and the adsorbed species. If you remember right back, I think from the first lecture or two, we talked about how the surface of the electrode is not just this pristine material in solution, but it will often be covered and have near it a large concentration of ions in excess of what you'd find in the bulk of the solution. And the presence of these charged ions at the electrode surface, and also to the presence of water molecules that can orient themselves at the electrode surface, tends to cause the electrode to have what we call a double layer structure. In other words, it has a capacitance, and that capacitance leads to charging current that we've already talked about, and that capacitance is a direct result of these adsorbed water molecules or solvent molecules and of ions on the surface. So in this chapter we're going to do, not in this lecture so much, but in the chapter itself, actually rigorously develop some theory for describing how to predict what molecules are going to be adsorbed on the surface and how to calculate the amount of adsorbed material on the surface and the effect that adsorbed material has on the surface. And this, we're going to kind of give you an outline of the chapter. I'm not going to go through all the math. It's certainly not that difficult. Some of it's actually quite tricky, but I'm just going to outline some of the results of the first part of the chapter, where they thermodynamically develop a theory for the double layer. And then we'll talk more about what happens when things adsorb on the electrode surface. This isn't just a simple electrochemistry problem that electrochemists are worried about. In fact, almost every area in which you have a surface exposed to some sort of a solution, you have to worry about a double layer. An example is colloidal materials. Those are really colloids because they have this double layer structure around it that prevents them from agglomerating into bigger structures. So colloids have double layers. Soil has double layers, so soil chemists are very interested in double layer chemistry. Biological membranes have double layers associated with them. So anytime we have a surface that can potentially carry a charge and is exposed to a solution that can have ions in it, we're going to have a double layer around it. Now, electrochemists are generally concerned with metal electrodes and the double layer, but again, most of the things we're going to talk about can be directly related to other types of materials that have double layers, as I said, soil particles and so on. So in this regard, we're going to be interested in understanding how the charge on the metal affects the double layer and how the ionic nature of the solvent affects the double layer. What happens when we change the concentration of ions in solution? What happens if we change the type of ion in solution? Does the more get adsorbed? Does less get adsorbed? How can we predict those sorts of changes? And in soil chemistry and things like that, similar considerations would be maintained. Now, the treatment that we're going to be talking about is based out of the book, but I found another book that's quite useful. It's actually quite ancient, really, at this point for textbooks. But it's written by a guy named Bockris, who's still around, and his associate at the time, Reddy, who's also still around. It's called Modern Electrochemistry. And I would recommend that if you're an electrochemist or interested in chemistry, electrochemistry at all, it'd be a good book to get. And it's very inexpensive in the softbound, $15 or $20. And we're going to be talking about in Volume 2, Chapter 7. I think that's Volume 2, yeah. And there's 2 volumes, and I would recommend the book. It's got 2 very readable treatments. Bockris talks about things in a way that it can be readily understood by even beginners in the field. So in this chapter, we're going to talk about a few things. One is we're going to start talking about what's this nature of the electrode solution interface, the double layer. What is it about? And how, then after we understand how it's about, how it's composed, what the physical properties of a double layer is, then we're going to see how this double layer can affect what we're really interested in as electrochemists. What's going to happen when we have this double layer and we do electrode reactions on it? How does it affect electron transfer? How does it affect the potential at the electrode surface? How will it affect perhaps the mechanisms of electrode reactions that are occurring at the electrode surface? And then we're going to think about some practical uses of this double layer and the fact that we can absorb things onto the surface of an electrode, and those might be used for things like modifying the properties. We've already seen where, say, platinum electrode is very active for hydrogen reduction. Maybe we want to modify the platinum surface by absorbing some molecules on it that make it less active for hydrogen reduction. We might want to absorb onto an electrode things like enzyme molecules to do analysis with. The enzymes will act as a material that will be a catalyst for certain biological materials, or as a detector molecule, something to do detection with. And so those types of modified surfaces are actually quite current topic in electrochemistry, and we'll discuss those a little bit as well. Well, let's first of all discuss the first part of that, and that's probing the nature of the electrode interface, of nature of the electrified interface. And again, we're discussing materials that we can actually change the electricity that's involved. So we can actually apply a voltage to these materials and so on. First of all, we're going to do a really important experimental technique, or at least in our notes, and we're going to talk about measuring surface tension. You're probably all familiar with the idea of surface tension. You know that all liquids have a surface tension. Water has a surface tension. It allows it to make beads up on, say, wax surfaces. It's forming this roughly spherical shape because that's the minimal energy configuration for that surface. The surface has more energy than the bulk, and so in order to minimize the amount of energy of the surface, it goes into a minimum area configuration, which happens to be a sphere under those conditions. And so many liquids have a similar minimum energy configuration. One of them is mercury. And so mercury, being a metal and a liquid, is a very useful material to understand the surface tension of the material. Since surface tension is something we can think about measuring, it actually is a good probe of the energy of the electrode surface. Surface tension is a free energy quantity. So by measuring the surface tension, we get direct access to the free energy of the surface itself. How can we do that? Well, first of all, we can try to calculate free energies, surface tensions, and we use lambda, small lambda, for that. And it actually can be done with pretty good thermodynamic rigor for metallic liquid electrodes, which really means mercury. For electrodes that are solid, like platinum or gold, the calculation of the surface tension requires some extra thermodynamic assumptions, which we won't really be able to get into. And it's very difficult experimentally to measure surface tension at solids. Just because they're solid doesn't mean there's no surface tension. There's still a surface tension, but it's not as easy to measure. Mostly because the metal has other problems. It doesn't have a uniform surface. It has grains, boundaries, and different sorts of exposed interfacial types, crystal edges and crystal planes. And also solid electrodes can have contaminants on the surface very easily, which change the surface tension. So we're going to talk about calculating that, again, usually with mercury only. It would work for any liquid metal electrode, which again is mostly mercury, although some alloys are also been used that are liquid at room temp. We'll talk about a capillary electrometer. Talk about Hyrovsky and how he was instrumental in developing ways to measure surface tension at mercury. And a guy named David Graham, we won't really talk about him, but he actually just want to mention that much of the modern measurements of surface tension on mercury owes a debt to David Graham, who did the work. We'll also talk about some theoretical models of the interface. There's 3 models that were developed in order of development. Helmholtz was a very early model, and then there was a model developed by a guy Gouy and Chapman, and then subsequently modified by a guy named Stern, now referred to the GCS model, which helps to explain a lot of things that we observe experimentally with a theoretical model of the thing. And it tries to explain things such as the effect of capacitance. How can we predict what the capacitance is of a particular surface? The amount of adsorbed material. And particularly important is what the potential distribution near the electrode surface is. And the other thing we're going to be interested in discussing is to probe the nature of the interface is to think about adsorption isotherms. And then we're going to talk about other methods that are not strictly electrochemistry, but can be used to understand electrochemical interfaces, particular things that are what the so-called ex situ methods. In other words, we take our electrode and we remove it from the solution and expose it to other methods. XPS, X-ray photoelectron spectroscopy, a high vacuum method. Auger, also another high vacuum method. LEAD, low electron energy diffraction, that's also a high vacuum method. These all rely on a pretty big assumption, so-called immersion assumption, where we can take a metal electrode and remove it from electrolytic solution and maintain the structure of the double layer in the absence of the bulk solution. And there's some evidence that that is roughly true. And even if it's not strictly true, there's still quite a bit of information you can get by looking at the surface and seeing what the structure is of the surface with an absorbed layer of material and with these high vacuum methods. And certainly quite a lot of important results have been obtained with those. Also, these are other methods, I guess. Other methods that we use besides ex situ that are so-called in situ, where we look at interfaces as they're exposed to the electrolytic solution. A lot of work is done with reflectance, where we look at the change in the reflectivity of a surface as we change the potential. And it turns out that sometimes quite significant change in the reflectivity of material occurs, and we can measure that and try to relate that reflectivity change with the surface tension or the absorbed material to it. Fourier transform infrared spectroscopy, very useful method. Raman spectroscopy, another very useful method. Recently, scanning tunneling microscopy has been used for these sorts of things, and another method called ellipsometry, which is essentially a reflectance method, but also measures polarity changes in addition to the reflectance, and very useful, especially for thin layers of adsorbed materials on surfaces.